This video is about a theorem in planar Euclidean geometry known as the Petr-Douglas-Neumann theorem after its discoverers, and it concerns n-sided polygons in the plane. It's a generalization of another theorem which has been known since the early part of the 19th century, often referred to as Napoleon's theorem, which concerns triangles. So the statement of the theorem is the following. For any closed planar n-sided polygon P0, define a sequence of closed n-gons, P1 up to Pn-2, such that the vertices of the jth polygon, Pj, are the apices of the isosceles triangles placed on the exterior sides of the previous one, Pj-1, with apex angles alpha sub sigma j chosen to be a multiple of 2 pi sigma j over n, where sigma j is any permutation of the numbers 1 up to n-2. Then the n-2nd polygon in this sequence is a regular n-gon whose centroid coincides with that of P0 and all the other polygons P1, Pn-3 in the sequence. The case of pentagons, n equals 5, is illustrated in the picture, with sigma, the permutation of 1 to 3, chosen as the identity permutation. So the initial pentagon P0 in this picture is A, B, C, D, E. And the next one, P1, is F, G, H, I, J, which consists of the apices of the isosceles triangles with angles equal to 2 pi divided by 5, or 72 degrees, placed on the exterior sides of all 5 of the pentagons of the pentagon. The next one, P2, is then constructed from P1 by adding isosceles triangles with apex angles twice 2 pi over 5, or 4 pi over 5, which is 144 degrees, onto the sides of P1. And P3, which is PQRST, is obtained by adding isosceles triangles with apex angles 6 pi over 5, or 216 degrees, onto the sides of P2, and that results in a regular pentagon. The case n equals 3, where P0 is a triangle, reduces to Napoleon's theorem, which says that the centroids of the external equilateral triangle erected on an arbitrary triangle are the vertices of an equilateral triangle. This is illustrated in the following diagram, where P0 is A, B, C. That's the original triangle. And P1 is PQR, and that's the triangle formed from the centroids, PQ and R, of the external equilateral triangle on each of these sides. For instance, BAF has centroid R, and ACE has centroid Q. The isosceles triangles of the Petr-Douglas theorem here are the ones which join the pair of vertices bounding each side to the centroid of the triangle above it. And the apex angles are 2 pi over 3, or 120 degrees. The general case is illustrated in this figure, which shows 4 of the 8 sides of an octagon. There's nothing special about the octagon. This is just to have a concrete illustration. And the isosceles triangles placed on them in this case have apex angles 2 pi over 8, or pi over 4. The indices sigma j on the apex angles alpha sigma j are suppressed here just for simplicity. The base angles are called beta sub sigma j in general, but here we've dropped the sigma j because this diagram could be at any stage in the construction. the perpendicular bisectors of each of the sides is joined to the apices of the triangles, dividing them into a pair of oppositely oriented congruent right triangles, for instance, this one and this one, whose angles, after we restore the indices to the alpha and beta, add up to pi. So there's a pi over 2, there's an alpha over 2, and a beta. That all adds up to pi. So beta is equal to pi minus alpha over 2 for each step of the construction. So now let's proceed to the proof. To do that, we first will identify the plane with a complex plane relative to an arbitrarily chosen origin and a Cartesian coordinate system in which x and y denote the real and imaginary parts of complex numbers z. The vertices of P0 are then identified as a cyclic sequence of complex numbers denoted z1 up to zn, with zn plus 1 conventionally chosen to equal z1 to make it cyclic. And all of the successive triplets of vertices are distinct, so we don't have a degenerate polygon, and the orientation corresponds to increasing indices. We similarly identify the successive vertices of the n-gon pj, for j from 1 up to n minus 2, with a cyclic sequence of complex numbers labeled with a superscript j. So z1j up to znj with the cyclicity condition included. And the 0th one is what we associate with the original polygon. We'll put a 0 on that for the sake of uniformity of notation. So by convention, what we mean by the exterior side of each oriented edge is to be on its left. If the apex angle happens to be more than 180 degrees, then it will actually be on the other side if it's a reflex angle. So the isosceles triangle, whose base is the I plus 1th side of the jth polygon, has vertices z superscript j plus 1i and zij, zi plus 1j. So this diagram omits the superscripts because this could apply at any stage of the construction. Now the vertex zij plus 1, for instance, this one, which is just denoted zi prime because the superscript is suppressed. So this vertex is obtained from the pair of base vertices zi and zi plus 1 by rotating the difference between the two, thought of as a two-dimensional vector, by the angle beta in the counterclockwise direction. So we take this base side, rotate it through beta to place it along the hypotenuse of this triangle, keeping the vertex zi fixed. So in terms of complex numbers, this means taking the difference between the complex numbers zi plus 1j and zij and multiplying them by a unit length complex number, e to the I beta j. That has the effect of rotating by the angle beta j. But that length, the length of this base is not the same as that of the hypotenuse. So we have to normalize it by dividing by the factor 2 times the cosine of beta in order to obtain the correct length of the hypotenuse. If we add that to zi or zij, we obtain the next one, and so the equation becomes zij plus the difference zi plus 1 minus zij multiplied by e to the I beta sigma j and divided by 2 cosine beta sigma j. So this can be simplified into the following form using the roots of unity. So omega here, just recall that omega is the nth primitive root of unity. And so the the angle alpha j, which is 2 pi j over n, if you take the complex exponential of that, if you take the imaginary exponential, that gives you the jth power of the nth primitive roots of unity. So the omega j's are all of the roots of unity. And that's what appear in this equation. So the second equality follows because the cosine of beta is, of course, e to the I beta plus e to the minus I beta divided by 2. So we can replace that in the denominator and then cancel out the factor e to the I beta in the numerator and denominator and use the relation between beta and alpha, which is this, to relate the imaginary exponentials, and that gives e to the minus 2I beta is equal to the negative of e to the I alpha, which is the negative of the root of unity omega to the power sigma j. So these equations, which describe the construction at each stage of the next polygon from the previous one, can be expressed in a more simple form using vector notation and thinking of the various vertices as the components of an n-component complex column vector. So this is the column vector. We place the various vertices as the entries of the column vector and label that boldface Z superscript j. For the P0, we'll also use the notation Z0, and the entries of that are the coordinates of the complex coordinates of all of the n vertices. Now, in order to express star in a nice vector form, it's going to be useful because of the shift in the indices from I to I plus 1 that appears. It's going to be useful to introduce the cyclic permutation matrix lambda with zeros everywhere except ones above the principal diagonal and in the left-hand corner. So that is a cyclic matrix whose nth power is the identity matrix. Then the equation that we have for the construction of the j plus 1th polygon from the jth can be written in a nice n-component vector form. This is completely equivalent to this equation because what the lambda does is to shift the ith component of zj to the I plus 1th. So it shifts it up by 1. So lambda acting on zj, its ith component is the I plus 1th component of zj. So that gives this term multiplied by the factor 1 over 1 minus omega to the sigma j. And the second term is just the original vector itself without any shift multiplied by minus omega to the sigma j divided by 1 minus sigma j. And the resulting vector is the j plus 1th vector formed from these components. Now, that is at one stage, but in order to get from the 0th stage to the n minus 2nd stage, we have to multiply all of these factors successively. So let's do that. If we go from 0 to 1, 1 to 2, etc., all putting in these factors, we get a sequence, and the whole product is a product of n minus 2 factors, each of them looking like lambda minus omega to the sigma j times the identity matrix, multiplied by a scalar factor 1 over 1 minus sigma to the j. And that gives us a compact expression for the components of the n minus 2nd polygon in terms of the 0th polygon. Now, whatever the permutation sigma is, it doesn't matter in what order these factors are written because they all commute. So we can write this expression in this equation in a slightly simpler way by just ordering them from 1 to n. And so this actually is equivalent to the equation. Now let's look at the condition that would imply that the Zn minus 2 vector consists of the vertices of a regular polygon. Well, let's give it a name. Let's call Zn minus 2w, and its components we'll call w1 up to wn. So what does it mean to be a regular polygon? Well, it's very easy from the picture to see that what it means is that um, at each vertex, if we take the two edges that that meet at that vertex, one is equal to the other in length, but the second one is obtained from the first one by rotating clockwise by the angle alpha, which is 2 pi over n. So how do we express that? Well, the vector wi to wi plus 1 is represented by the complex number, which is the difference between the two, omega I plus 1 minus omega wi plus 1 minus wi. So rotating it in the clockwise direction by angle alpha is the same thing as multiplying it by omega inverse, because omega is the e to the I alpha, and that will give a counterclockwise rotation. This is a clockwise rotation, so it's the inverse. So the rotation of this vector by alpha in the clockwise direction in terms of complex numbers is given by this product. And that has to equal this vector, which is the difference between the complex numbers wi plus 2 and wi plus 1, so we get this equality. That has to hold for all I from 1 up to n, and continuing the sequence cyclically, so n plus 1 is the same as 1, and n plus 2 is the same as 2. So that equation can also be written in a vector form. Only here we have a shift of the indices by 2. Here it's a shift by 1, and here it's again a shift by 1, and here it's no shift at all. So this equation written as a vector expression using lambda, we have to have lambda squared to shift by 2. So this term wi plus 2 is the ith component of the vector lambda squared w. And minus I plus 1, wi plus 1, is the ith component of the vector minus lambda w. And we have the factor omega inverse. And again, we have a shift by 1. So that has to multiply lambda w. And we have no shift at all. So that just multiplies w. And this equation is equivalent to this equation in component form. Now we can factorize this polynomial. It's a quadratic polynomial lambda, and it can be very easily factorized. So the same equation can be written in the nice form of the product of lambda minus the identity matrix times lambda minus omega inverse times the identity matrix acting on W gives 0. Now for what follows, it's going to be convenient, or it'll be more apparent to rewrite this equation, replacing the number 1 that is the coefficient in front of the identity matrix by omega to the n. Since omega is the nth primitive root of unity, omega to the n is 1, so we can put in an omega to the n in this factor instead of 1. And similarly, omega to the minus 1 can be replaced by omega to the n minus 1 for the same reason. So the equation with the 3 stars can also be written, it's exactly equivalent to this equation, where we put in omega to the n here and omega to the n minus 1 here. Why have we done that? Well, it's because all of these factors of this type, are what come into the expression for the n minus second polynomial, n minus second polygon. So we had the product of z times lambda minus omega to the j times the identity, where j went from 1 up to n minus 2 times this scalar factor. Now these two terms are of the exact same form as this, and what we have to do is to show that when they act upon this vector w, they give 0. So all we have to do to write that equation is to replace this product of n minus 2 factors, lambda minus omega to the j, by a product with n factors, by putting in the extra 2 terms, omega to the n minus 1 and omega to the n, that annihilate w if it's a regular polygon. So the equation for a regular polygon is given by this. And this equation is indeed satisfied simply because the polynomial identity which factorizes zn minus 1 into its elementary factors consists of the difference of z and the roots of unity. So that identity is true. But this is true for any symbol z which commutes with 1. So we can take this expression and replace z by lambda, giving this expression, where lambda has replaced z and the identity matrix has replaced the number 1 multiplying omega to the j. So we have a factorization equally well of this, the product of these factors reconstructs the difference between lambda to the end and 1 and the identity matrix. But lambda to the n is equal to the identity matrix because it's a cyclic matrix of cycle n. So that difference really is 0, and we just proved that W, therefore, given by this formula, is a regular polygon. So the last part of the theorem concerns the centroids of all of these polygons, and we're supposed to show that they're all equal. Well, that's very easy. To get the centroid of, these are all the centroids of the various polygons. To get these, what we do is average the vertices. The position of the vertices added up and divided by n is the position of the centroid. So that's equivalent to saying, take the column vectors with each one of these and multiply them on the left by the row vector whose entries are all ones normalized by 1 over n. So this is the formula for the centroid. This element, because it's all constant entries, all of the entries are equal. That means it's invariant under any permutation, and that means that it's a left eigenvector of the permutation matrix lambda. E times lambda is equal to E. It also is a right eigenvector, but we don't want that. We need the relation E lambda is equal to E. So now let's take the recursion relations that give the j plus 1th vertices in terms of the jth vertices. That's this, and multiply it on the left by E to get our centroids. So if we multiply zj plus 1 to the left by E, we'll get exactly the centroid of the j plus 1th polygon. But if we multiply the second term, the second factor here, by E, well, E lambda gives you back E. So we'll get an E here if we multiply on the left by E. Here's the E. And, of course, the identity matrix just reproduces E. So we can bring the E through from this parentheses to multiply Z to the J. But this, because this is an eigenvector with eigenvalue 1, this is replaced by 1. So we get in the numerator 1 minus sigma to the omega to the sigma j. And we also have in the denominator 1 minus omega sigma j. So these two factors cancel, giving us EZJ, which is the centroid. So that means the centroid of the j plus 1th polygon equals the centroid of the jth, proving that all of the centroids are equal. And that ends the proof of the theorem. Here are the references to the original papers in which these results were discovered and published. And there's also reference, the picture at the top of the Pentagon, this nice picture, is in the Wiki Commons. So it appears in an article in Wikipedia about this theorem, and the author of the diagram, we're not obliged to cite it, but the author, his name is Krishna Chandran Van. I hope I pronounced that correctly.